Hey everybody, today we're going to talk about the hypergeometric distribution. And a couple of things before we begin. I expect you to be very familiar with the binomial distribution because the hypergeometric is very much related to the binomial, but there are some differences, and so I'm going to talk about the similarities and differences. And I expect you to be very familiar with the choose function, also known as the combinations formula, also known as the binomial coefficient. And in general terms, this is going to give us the number of ways of picking X items from N distinct items. And this plays a huge role in the hypergeometric. If you understand what this is, then the hypergeometric flows very naturally, and I wouldn't even have to do this. We've probably done, when we have done, probability calculations that were in spirit hypergeometric probability calculations. We just didn't call them that. So again, this is a formula that gives us the number of ways of picking X items from N distinct items, and it involves factorials here. N factorial over X factorial times N minus X factorial. I am not going to get into the details of this. I expect you to know what this is and do a little reading or watching to figure that out before we talk about this, because it plays a fundamental role. So the number of ways we can pick X items from N items. There's a choose function in R. Other software has functions. Your calculator likely has a function that will calculate it for you. Okay, on to the hypergeometric here. Hypergeometric is very strongly related to the binomial distribution. Rises in a slightly different setting here. And let's look at a simple example before looking at the formulaic approach here. We have kind of a classic hypergeometric scenario where we've got an urn with 4 red balls and 6 blue balls, and we're drawing 3 balls without replacement. It's going to be fundamental to this. And we want to know the probability there's exactly 2 red balls drawn. So if, say, we let X represent the number of red balls, we want to know the probability that X takes on the value 2. But this without replacement is extremely important to us here. Extremely important to us. If it was with replacement, then the probability of getting a red ball on any individual draw would stay the same regardless of what had happened before. Our probability of getting a red ball on the first draw, say, just very first draw, well, there's 4 red balls altogether, right? And there's 4 red balls and 6 blue balls, so 10 balls altogether. And the probability of getting a red ball on the first draw, say, is 4 out of 10. But if, say, if the first ball we draw is red, then on the next draw, the chance we get a red ball is 3 out of 9. There's only 3 red balls left out of 9 balls total. And if, say, we got a blue ball on the first draw, then the probability of getting a red ball on the next draw is 4 out of 9. So on the second draw, the probability of getting a red ball is going to depend on what happened on the first draw. And so these draws are not independent. The probability of getting a red ball on any of these draws from this urn is going to depend on what happened before. So we do not have independent draws from this urn. And the probability of getting a red ball on any draw is going to depend on what happened before. So that means the binomial isn't going to work, because a fundamental aspect of the binomial distribution is that we have independent trials. We do not have that here, and it's a dependence in a very specific way. We are drawing from a source here that contains, in this particular situation, 4 red balls and 6 blue balls. But it will be analogous to this in general, drawing from a source that contains some successes and some failures. So we'll look at the probability mass function for the hypergeometric in a second, but let's just figure this out. Let's think about it. If in this situation we are drawing these 3 balls without replacement from that source that has 10 balls altogether, how many ways are there of doing that? Well, from 10 balls, we are choosing 3. So there's 10 choose 3 ways of doing this. That's the total number of ways of picking 3 balls from 10. Okay, each one of those is equally likely. If we're doing this randomly, we're reaching in, pulling out a ball, right, shaking it up, pulling out another ball, this sort of thing. These 10 choose 3 ways of picking those 3 balls are all equally likely. And so from our basic probability rules, what we need to find the probability that there are 2 red balls, the numerator simply has to be the number of ways of getting exactly 2 red balls. And how are we going to do that? Well, there's 4 red balls in total. So from those 4 red balls, we must pick 2. Okay. Feels like we're done? We're not done. We're not done. Okay. Because this 10, choose 3 in the bottom is all the possible ways of picking 3 balls from 10. And this, okay, gives us the ways we can pick 2 red balls from the 4, but there's one missing ball that we have to account for. So if we want exactly 2 red balls, we have to pick 2 red balls, but also from the 6 blue, we have to pick 1. From those 6 blue, we have to pick 1. And if we go through and we do all of this, we're going to see that that's 0.30. And there's 30% chance of getting exactly 2 red balls in that draw. Okay, so when we do this, it's just sort of good to think through these things, I think, rather than rely on the probability mass function. And just think through this whole idea. From the 4 red balls, we had to pick 2. From the 6 blue balls, we had to pick 1. And that's going to be on the numerator, give us the total number of ways we can pick 2 red balls. Exactly 2 red balls. And the denominator is the total number of ways we can pick 3 red balls from 10. And we're going to be using that logic along the way. Now, we might notice one thing here. 4 plus 6 is 10. 2 plus 1 is 3. It's going to be like that. Okay. It's going to be like that in the formula, and it's going to be like that when we do that. So it's something to take note of as we go. Now, had the drawing been done with replacement, if it was with replacement, then it's a binomial setting. If the drawing was with replacement, it would be a binomial setting. And if we had we want the probability that x takes on the value 2, well, what are we doing? We're drawing 3 balls. We want to know the probability of getting 2 successes in those 3 draws. The probability of getting a success is going to stay 4 out of 10 the whole way. So I'm just going to put 0.40 here, or 0.4, let's say, and that's got to be squared. 0.4, the probability of getting a success, raised to the second power, and then the probability of getting a failure, 1 minus 0.4, let's just put it in here as 0.6, and we have to pick one of those. If we were to do that, 3 decimal places here, we get 0.288. So we notice here that the 0.288 from the binomial, the with replacement, implicitly the with replacement case, that's fairly close to the without replacement here. Sometimes it will be close, sometimes it will be not so close, and we're going to look at situations where we might approximate the hypergeometric with the binomial, and why we might do that in a little bit. But sometimes the binomial will be quite close, sometimes not so close. Right? We'll look we'll look at that in a little more detail a little bit later. But without replacement is the fundamental thing here. And for hypergeometric, of course, it has to be just this scenario, picking from this source that in this case had the red balls and the blue balls, but it'll always be analogous to that. We got some successes and we got some failures. Okay, so let's look at a more formal introduction to that. So the scenario is, like I've been saying, we're randomly sampling n objects without replacement from a source that has a successes. So little a represents the number of successes in the urn or in this source that we're drawing from, and capital N minus a failures. So we have a total of capital N objects that we're drawing from. Total of capital N objects that we're drawing from, and we're drawing little n objects. And we're going to let x, capital X is going to represent the number of successes in those n objects that we draw. Okay, if that's the case, then X has the hypergeometric distribution, which is just the formulaic representation of what we just thought through up top. This is the probability mass function here of our hypergeometric distribution. The probability the random variable x takes on the value little x. Well, from those a successes, we have to pick x. And from the n minus a failures, we have to pick n minus x, because we're picking n things in total. And total number of ways of doing that, n objects in total. From the n objects in total, we are picking n of them. I cannot stress this enough, that when you're doing these types of problems and asked for probability problems, that you don't think of this probability mass function like this. You think it through like we did with the red and blue balls. I contend that every single person on the face of the earth, if they are capable of using this formula, they are more capable of simply thinking it through. And if you ignore me and say, I'm going to use the formula anyway, and you don't know, understand how to use it, and you're making mistakes, that's on you, right? Use my way. If you want to use the formula, fine, but then you better be getting it right. Okay, so one thing, when we're talking about probability mass functions, this isn't enough to just give this, because this doesn't hold everywhere. This doesn't hold for n plus 7, or when x is n plus 7, or x is 0.6, because we can't get a 0.6 successes. So it holds for certain values. And when you list a probability mass function, you've got to say what values this works for. Now, you might remember for the binomial, right? The binomial, when we were doing the binomial, it was quite simple. The possible values of a random variable were 0, 1, and the whole numbers up through n, right, for the binomial. This is similar to that, but there's some complications. So it might look a little bit ugly here, but there's a couple of things that are easier to think through rather than, don't memorize this. Please, don't memorize this. Let's think it through, though. Okay, we're drawing n balls from this source. We cannot possibly have more successes than little n, right? We're drawing little n balls. We cannot possibly have more successes than the number of balls or objects that we're drawing. So the total, the value that x takes on here, the maximum value x takes on, can't be bigger than little n. That makes sense, right? But wait, we've also got a total number of successes in that population. The total number of successes we get in the sample can't possibly be greater than the total number of successes from the source we're drawing from. So the number of the successes, the maximum number of successes that we get, has to be the minimum of the number of successes in the population and the number of balls that we're drawing. Okay, on this other side, a little bit easier or a little bit harder to think of, but it's really the same thing in terms of the failures here and that sort of idea. One, we know, of course, it's a count of something. Our random variable x is representing a count of something. So the number of successes cannot possibly be less than 0. That's the smallest number of successes we can get. That's 0. This bit's a little trickier to think about. But n minus a. N minus a is the number of failures. This bit is the number of failures in our population. The maximum number of failures we get cannot possibly be larger than the number of failures in the population. So this is the maximum number of failures we could get in our sample. That's one possibility here. We know it cannot, the number of failures we get cannot be larger than this quantity, the number of failures in the population. So then the number of successes cannot possibly be smaller than little n minus this max number of failures. Little bit harder to think about from on the other side, but really the same thing, okay? Really the same thing. And so our minimum number of successes can't be less than 0, and it can't be less than little n minus capital N minus a, so it can't be less than, the minimum value is going to be the maximum of those two quantities. A little bit harder to think about. This all ports over here a related way, just a little bit more complicated. Okay, not a huge deal, that part. Now, the mean and the variance. Now, we might remember one fundamental thing here. We'll relate that to the binomial. For the binomial random variable, The mean is n times p. And our variance is n times p times 1 minus p. Okay, that's a fundamental thing we talked about for the binomial random variable. P is your probability of success on any individual trial for the binomial. And this stuff here is very, 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 very similar to that. This is like that. Little n times the proportion of successes in the population. There's A successes in the population over capital N objects. And so this is very much like that. Little n times the proportion of successes in the population. And the variance is very much like that. This bit is very much like that, right? Our n times p sort of thing times 1 minus p sort of thing. Very much like that. And we have this extra little thing over here. And that is coming up from the fact, if we look at this, what's going to happen is this is going to be a little bit lower. Our variance is going to be a little bit lower. It all depends on the precise values, but it's going to be lower than the binomial variance. And we'll look at an example of this in a minute. But one of the things that's happening here, we might imagine, for the hypergeometric, it's going to be a little harder than with the binomial. The hypergeometric is going to be a little harder to get those extreme values. It's going to be harder to get all successes or all failures, say, than if it were a binomial setting, because for the hypergeometric, it's without replacement. So let's say if we drew a red ball and we put it to the side, it's now harder to get another red. If we drew another red, then it's even harder to get a red on the third draw. So it becomes harder and harder to get those extremes. So there's this sort of mitigating thing happening in there for the hypergeometric, where if you're getting successes, it's harder to get another one. And if you're getting failures, then it's easier to get a success. And so we have a tendency to get these values sort of near the middle-ish, if I can say that. And what that means is your variance is going to be a little bit lower. Again, we'll do an example of that. And this is related to something we call the finite population correction factor that comes up in more broadly in sampling theory, this sort of idea. But overall, I want you to sort of see how this relates to the mean and variance of the binomial. And one reason for that is that we are going to be using, at times, the binomial distribution to approximate the hypergeometric. Okay, so we're going to look at an example, maybe illustrating some of this sort of notion. We have electric yellow cichlid, colorful freshwater fish that some people like to have in their aquariums. And it's difficult to sex, so hard to tell whether it's male or female. And have a little picture. These are not electric yellow cichlids, but they're yellow cichlids, okay, with a license to use the picture. So a little bit like this, electric yellow, a little black on them. They're cooler. You can look them up. No offense to these little fishies. They're nice. Okay, so we have a tank containing 4 females and 5 males of the species. And a new breeder buys 3 of this fish. So they're going in, they say they want to buy 3 of this fish, and let's say they just don't have any idea. Difficult to sex to the point in this scenario that these 2 people don't know, either the buyer or the seller, right? They don't know. They can't sex these fish, and they're just randomly going to draw 3 fish from this source that contains 4 females and 5 males. And so with these 3 fish, we can think of as a random sample. Let's say they're just drawing them randomly from the tank. And to a reasonable approximation, we can think of the 3 fish that we get as a random sample. Okay. So the question then, what is the probability there are 1 or 2 females? So exactly 1 or exactly 2 females in this sample of 3 fish. Why, who would care about this? Wait a minute, I care about this if I'm the person buying and I'm a new breeder here, because I'm getting 3 fish and I want at least one male and at least one female, if I'm hoping to pull something off here with the electric yellow cichlid and have some little ones come out eventually here. So this would be a relevant point, a question for this a person in this setting sort of thing. We might be interested. What's the probability you get one or two females in that particular sample? So the number of females is going to be a random variable with a hypergeometric distribution. We've got the same situation as red balls and blue balls, except now we've got electric yellow cichlids, and they're either male or they're female, right? So we've got the same type of thing. So number of females would be like the red balls that we were picking before, and that's what we're interested in. So we want to know the probability that your number of females is either 1 or 2. Okay, well, it's a discrete probability distribution, so what we're going to have to do is figure out the probability that x takes on the value 1 and add that to the probability that x takes on the value 2. And we just use the probability mass function for this, the probability mass function for this, which we can do in here, right? We can do this here. Okay, so when we are working through all of this, probability x takes on the value 1. If we look at this, from the 4 females, we have to pick 1. From the 5 males, then we have to pick 2. From the 9 fish, we're picking 3. Again, we might notice 4 plus 5 is 9, 1 plus 2 is 3. On this side, for the probability x takes on the value 2, from the 4 females, we have to pick 2. From the 5 males, we have to pick 1, and we're picking 9 from this overall, we're picking 3, from the 9 fish in total. And so if you put this into your calculator, or we could put this into R using either the choose function. When I'm doing this in R, I like to use the choose function, and just put it out there itself, right in there, and think it through, and like 4 choose 1, 5 choose 2, 9 choose 3, these types of things, then I'm confident that what I'm doing is correct. There is also a D hyper and a P hyper function in R. The D hyper giving us probabilities, our probability mass function. That's what it is for the input values, except it's a little tricky for the hypergeometric because we've got 4 whole numbers there, and we have to say, okay, which order did R want these in? And it's a little tricky, but it can be done. Just every time I'm doing it in R, I have to look it up and say, okay, which order does R want this? And so then I typically just use the choose function. Okay, but we end up with 0.8333. All right. And if we're doing this, we've got that. We've got our hypergeometric probability mass function. We've worked through it. We worked out now the probability that this person buying these 3 fish is about, and the probability they get 1 female or 2 females is about 0.8333. Okay, now that is the hypergeometric situation with the without replacement case. Now you might notice I never said without replacement here. Sometimes it's just flat out implied. The person's going in and they're buying 3 fish. Hey, I'd like 3 fish. I'm paying you for your 3 fish. Here, man, here's a fish. I just sampled it 3 times. Is just not something a seller of fish will be able to get away with. Okay, you're buying 3 fish. That means 3 fish. So it doesn't have to explicitly state without replacement every single time. Sometimes that's just implied by the nature of the problem. And so this was for the without replacement case, the hypergeometric. Now what about if we were to say for the binomial? For the binomial, same idea. And we could do this in R quite quickly with our R functions and get the probability and just work through the same type of way. We're saying our probability of getting 1 or 2 females then works out to this. If we were to do this in R, comes out pretty fast, 0.7407. Wait a minute, 0.7407 is the binomial with replacement scenario, and the without replacement scenario was 0.833, right? So binomial was about, had a probability of about 0.74. And that's quite a bit different from most practical situations. 0.833, 0.74 is quite different. Those are different probabilities here. Our probability for the hypergeometric was quite a bit larger than that. So sometimes the binomial is a good approximation to the hypergeometric, and sometimes not so good. And let's just sort of see what's going on here and think about this. If in this situation we were to calculate the probabilities for the number of females here. Okay. So what we see in this setting, worked out the probability of 0 or 1 or 2 or 3, these ones here, right, for all the possible values for a sample of size 3. And what do we notice? Like I was saying earlier, the probability of getting an extreme like 3 or 0 is lower under the hypergeometric distribution. It's harder to get the extreme values. It's harder to get 3 females, because when you pick 2 females, say, on the first 2 draws, it's hard. There's 2 fewer females to pick the next time. So it's harder to get that third than it would be under the binomial, which is assuming those the trials are independent and your probability is always the same as it was on the first draw. So what's happening here in the hypergeometric is it's harder to get these extremes, but the probabilities, of course, have to add to 1. So conversely, it's easier under the hypergeometric to get sort of these middling values. And so we tend to have a higher probability of these types of ones, a lower probability in the extremes. And that can be quite a big difference. And so when we do that, and again, when we do that, if we scroll back up to our variance scenario here, scrolling back up to our variance scenario, that's what's happening. We're getting the higher probability of those middling sort of values, lower probability in the extremes, leading to this lower variance. But we might notice, just by looking at this, we might notice, so wait a minute. If we were drawing, let's say, from a source with 10,000 objects, and we were only picking 3 from there, well, this quantity at the end is going to be pretty close to 1, right? If you're only picking a few things from a source that has a large number of things, this quantity is going to be sort of, closer to 1. This variance is going to be similar to the binomial. And just intuitively here, when we're doing this, if you're picking only a small number of objects from a source with a large number of objects, well, your probabilities aren't going to be changing that much from trial to trial, depending on what happened before. So intuitively, I think, if we think of this, that if we're only drawing a small number of objects from a population that has a large number of objects, let's say, well, then the binomial probabilities and the hypergeometric probabilities are probably going to be pretty close. So let's look at this here. If we did this same example, where we're drawing 3 fish, but a much larger tank. So we had 4 females before and 50 males. Now we've got 40 females and 50 males, right? So the probability of getting a female on the first fish, I'm leaving that the same. That's still 4 out of 9, right? There's 4 females and 40 females and 50 males. So it's 40 out of 90, or 4 out of 9 is our probability of getting a female on the first draw. And then on the next draw, if we did get a female on that first draw, probability of getting a female on the next draw is 39 out of 89, just pretty close to 4/9. And if we went through then, just using, that was a bit of a hand-wavy argument, but if we did this calculation again under this new setting, we would get a hypergeometric probability of this. The binomial wouldn't change because if it's with replacement, that situation doesn't change. Binomial would have this probability of 4 out of 9 on any given trial. And for the binomial probability, it would be the same as that one we did last time, about 0.7407, which is pretty close to the probability we got using the hypergeometric distribution. And so that leads us to a rough guideline here. So I've been doing a little hand-wavy stuff overall. So rough guideline here, that the binomial can provide a reasonable approximation to the hypergeometric if we're not sampling more than 5% of the population. That's not a perfect guideline. Okay, it's not a perfect guideline. It's a rough sort of approximation for us. And I hope the logic is clear here that if you're only sampling getting a small sample from a large population, well, then those probabilities aren't going to be changing much from draw to draw. When you're doing it without replacement, sure, they'll be changing still. Sure, fundamentally, it's still hypergeometric type of setting. But those, even though there's a dependence in the trials in this, and our probabilities will be of getting a success is going to change depending on what happened on previous trials, not going to change too much. And so our binomial probabilities are closer to can be quite close to the hypergeometric. Now, why does this matter? Why does this matter? Why don't you just do the hypergeometric every time? Well, it matters in various spots, including statistical inference, because the hypergeometric is a little bit more complicated. So if we go back up here and we see stuff like we had when our mean and variance. Well, for the hypergeometric, we've got these a little bit of a problem. It's a little bit more complicated scenario now, and the binomial is a little easier to deal with. And our formulas for things that when we're working with the binomial are a little bit cleaner and simpler to work with. Simpler rather than cleaner. They're simpler to work with. And so let's say we're drawing a sample of 1,000 people from a population of 30 million. And we want to know the proportion of the entire population that has a certain characteristic, that approve of the way the prime minister is doing their job, or what have you. Well, maybe it's truly a hypergeometric type of setting, but boy, the difference between hypergeometric and binomial is just going to be pretty much meaningless in practical scenarios if you're drawing only 1,000 people from many million, say. And the binomial is a little bit easier to deal with. And so we might just go, binomial is pretty close enough in this spot. Maybe in its nature, something's truly a hypergeometric. We'll go with binomial in this setting. So we might do something like that at times. Now, the situation generalizes quite easily. This hypergeometric generalizes quite easily to where to the situation where we have more than two groups, more than just successes or failures. Like in this case, maybe not just the red balls and the blue balls, but red balls and blue balls and yellow balls. And we want to know the probabilities of all those different kinds of things. And that's something we call the multivariate hypergeometric distribution. It's a general, quite straightforward extension to this sort of thing. But I'll leave that talk for another day.